Section 2.6, Implicit Differentiation. Prior to this point, all of the functions we have seen have been described by one variable. So we always were looking at something as y equals something else. Some functions, however, are defined implicitly by a relationship between x and y. Here are a few examples. X squared plus 4y squared equals 4, or 3x squared plus y squared squared equals 100xy. Fortunately, we do not have to solve this equation for y in terms of x. Instead, we can use a method of implicit differentiation. Implicit differentiation, what we would want to do is differentiate both sides of the equation with respect to x. Since we're doing this with respect to x, we might need to use the chain rule. Then, after, we will solve for y prime or dy dx, depending on how you write that up. So first, if we take a look at 1a, our equation is x squared plus 4y squared equals 4. So first, we're going to differentiate both sides. So with respect to x of the left side, and differentiate with respect to x on the right side. So when we do this, on the left side, we get 2x plus 8y. This dy dx is coming from the chain rule. Y is a function of x. So we need the chain rule to be applied to the function y. So essentially, the 8y, we took the derivative of the y squared, and then we needed to multiply by the derivative of the inner function, and that's whatever y happens to be. We don't know what y is defined explicitly. We only have the implicit function written above. Once you differentiate both sides, we now will solve this equation for dy dx. Continuing up above, we move the 2x over, so it's negative 2x, and then we divide by 8y. So our derivative with respect to x, derivative of y, is negative x over 4y. Part B asks us to find the equation of the tangent line to this ellipse. This equation that you see is the same equation from letter A. So if we have to find the equation of the tangent line, we would first need to find the derivative at that point. In part A, we found the general derivative. So first, we're going to look at this point, which we know is xy. So what we need to do is evaluate the derivative that we just got in A at the given point. And this will let us find the slope of the tangent line at that point. So dy dx equals negative, our x value is the square root of 2, and our y value is negative 1 over the square root of 2. We simplify, and we get 2 over negative 2 over negative 4, which is 1/2. So we're going to use the point given to finish the equation. So we know y minus y1 will equal the slope times x minus x1. We plug in our y again, plug in the slope we just found, plug in our x. You can leave it like that, or you can continue the simplification to get it as a y equals form of a line. Once you simplify, you get your final answer, which is y equals x over 2 minus the square root of 2. Let's take a look at another example. They're asking us to find y prime if this was the equation we're looking at. We again notice that it would be difficult to solve this for y, which is why we want to do this implicitly. So like before, we're going to take the derivative with respect to x of both sides of the equation. When we do the left side, chain rule comes into play. The 3 was left by itself, but dealing with the 2, we bring the 2 in front, changing our power to a power of 1. Leave the inside alone, and then we're going to need to take a derivative of that inside, giving us 2x plus 2y, and we can't forget the y prime, or the dy dx. And this again is chain rule. Y is in and of itself a function, so we need to take the derivative of that function. And then the right side, we notice we have x and y, so we're going to have to use the product rule, which says leave the first, find the derivative of the second. So you'll notice at this point the derivative of y is 1, but by chain rule I must include that dy dx. Then plus take the derivative of the first, which is just 1, leave the second alone, and that's where the y is. So we simplify. And after simplifying, first combining those, still simplifying, we're taking that yellow piece and multiplying it to the quantity x plus y dy dx. That's what you see here. Then on the right side, we still have the same thing. Now that everything's been multiplied out, we notice that the 2 underlying pieces both contain dy dx. So we want both of these pieces on the same side and everything else on the other side, because now we're trying to find or solve for dy dx. So I move the 100x dy dx over to the left side, and then I move the 12x times x squared plus y to the right side. And then both on the left side have the dy dx, so I'm going to factor that out. Now that I have factored that out, I will take the right side and divide, continue up here. So I divide the right side by the product on the left. Then I also notice that this can be further simplified if I divide everything by 4. Or equivalently factor out a 4, and then the 4's will cancel. So your final answer for the derivative is 25y minus 3x times x squared plus y squared, divided by negative 25x plus 3y times x squared plus y squared. Part B asks us to find the tangent line to this curve. There's a picture here for you to see how that graph would look. We're trying to find the tangent line drawn at 3, 1. Similarly to what we did in number 1, 3 is our x and 1 is our y. So first we're going to plug into our derivative function from part A. So rewriting that derivative function so we have it as reference. We're going to plug in the x's and the y values, and I'm color coding that to make it easier for you to follow along. And then We simplify, and we get a slope of 13 over 9. We're going to use the slope 13 over 9 and the point 3, 1 to write the equation of the tangent line. We're going to plug in the point and the slope. You could have stopped it at that point, or you can continue solving so that your equation is y equals. Final answer for the equation of the tangent line is y equals 13 over 9x minus 10 over 3. Sorry. There we go. Let's continue along practicing implicit differentiation. Here's another example utilizing trigonometric functions. So we're going to take the derivative of both sides with respect to x. You should notice on the right side that there is a multiplication there, so we will have to use product rule. When we look at the left side, derivative of sine is cosine x. And then we have negative sine y times y prime. That's the derivative of cosine y. We need to multiply by y prime because of the chain rule. On the right side, as I mentioned, we're going to have to use product rule. Derivative of the first, leave the second alone, plus leave the first alone, derivative of the second. And in taking the derivative of the second, because it is y, we must remember to include our y prime because of the chain rule. Y is a function, so we need the derivative of that function. Notice that those two pieces are the ones that contain y prime. So I'm going to bring those to the left side. And I'm going to bring everything else to the right side. And then I'm going to factor out the common factors. And then I'm going to divide, pulling out the sine y. I just caught an error. Looking at this top part, this derivative of cosine y should have been a negative sine y. So I just starred that for you. Everything in the subsequent equations are correct, but there should be a negative there. Now then, everything else will follow, and your answer for y prime is still the same. We can use implicit differentiation to solve for second derivatives as well. It's a little bit more work, but it can still be done. So the first thing we're going to do in number 4 is find the first derivative. So we bring down the 2, and we get 18x plus 2y, y prime equals 0. We solve for y prime, and there's our first derivative. Y prime equals negative 9x over y. When we're finding the second derivative, you'll notice that it is a quotient, so we will have to use the quotient rule. So we're going to take the derivative of the first derivative. We're going to factor out a negative 9, and then we're going to use the quotient rule. Leave the bottom alone, derivative of the top. Since we pulled out the negative 9, we're just looking at the derivative of x, which is 1. And then minus, leave the top, derivative of the bottom. Notice I included the y prime. Derivative of y is 1, but I must include the y prime due to the chain rule. Divided by the bottom squared. Then I simplify the algebra, and you're going to notice that for y prime, I have plugged in what y prime is. Purple equation on the left, which is negative 9x over y. That's what makes it a little bit different, is when you're using implicit to find higher order derivatives, you will have to substitute in both the derivative and, as you're going to see in a moment, the function. So we continue to simplify and simplify again. Notice that I just highlighted that 9x squared plus y squared is equal to 9. Notice that that's in the numerator of our simplified version. So we're going to plug in 9, the highlighted part, and then simplify, and we get 81 over y cubed. That is the second derivative. So as I mentioned, on higher order derivatives, using implicit differentiation, you will have to plug in what you had previously. This is the end of section 2.6.